Section 6.3, Volumes of Solids of Revolution. A solid formed by revolving a region about a given axis is called a solid of revolution. Let's look at some examples to see how we can use the techniques of the last section to find the volumes of these special solids. So for example, let R be the region bounded by y equals x squared and the x-axis for x between 0 and 4. Suppose R is rotated about the x-axis to form a solid which we'll call S. Find the volume of the solid S. First, let's get our bearings by looking at a picture. So here is the region. It's the region bounded by y equals x squared, the x-axis, for x values between 0 and 4. So this is much like when we found the area under a curve or the area between two curves. This is forming the region. Now this is not our solid. We're going to generate our solid by revolving this region about a given axis. And here we said that we're going to revolve this around the x-axis. So I'll indicate my axis of revolution here and the direction that I'm revolving. When we do that, we generate this three-dimensional solid, this funnel-shaped object that looks like this. Now notice we do need to have a picture to get our bearings of what's going on, but it doesn't have to be the greatest picture. We don't have to have great artwork, but we do have to understand what our region is, what our axis of revolution is, and the solid that we're generating. Just a rough picture of what the solid looks like. Okay, so when we do this, what we want to do is since we rotated this around an x-axis, we see that if we slice it in the direction that's perpendicular to the x-axis, in other words, if we make these vertical slices, that we'll get little discs. And I just drew one of them because I didn't want my picture to get too busy, but envision many of these little discs. It's very much in the spirit of the last section, except here we know what the geometry is going to be. Because it's a solid of revolution, if we slice it in the correct direction, we can take advantage of that circular symmetry, and then we have a nice friendly geometry for the slice. So notice I draw one representative slice. The slice is located at a variable distance x. I say a variable distance because there will be some slices here, 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 and here. So this x is really dynamic, and it moves from here all the way across our solid. But if we pick a representative slice, it sits here at x. And when we do that, we see that the important things going on in this slice is that it has a thickness, delta x. It's in the x direction. The thickness is in the x direction. And we see that this is a little disc. So in keeping with what we did in the last section, the volume of the slice is the area of the face times the thickness. But we have a very nice geometry of our slice here. It's just a little disc. So we know that the area of the face is just the area of this circle. We know the thickness is delta x. So we just find the area of this circle, which is pi times the radius squared. I indicated the radius here. It's a variable radius. Notice the radius of the slice that's over here will be much larger, and the radius of the slice here will be much smaller. So we have a radius that varies as x varies. But if you give me an x, we can find the corresponding y. And notice this y is not random, but rather it's following this curve y equals x squared. And so here we see if the radius distance is y, then pi times the radius squared times delta x is going to be the volume of our slice. And now we want to read our keys. Since the thickness is delta x, we know we have to have the rest of the things in this in terms of that variable. So since this is a delta x, we need to get y as a function of x. Well, thankfully, we have this right here at our disposal. We know that this y is equal to x squared. So we replace y with x squared. It's still squared from finding the area of the face. And so now the volume of our slice is pi times x squared, quantity squared, delta x. And therefore, to get the total volume, we just accumulate or integrate the volumes of our slices. So the total volume is the integral. Again, we're going from where our slices are ranging from x equals 0 to x equals 4 as we march along with our slices here. So we're going to integrate from 0 to 4, and the volume of our slice was pi x squared, quantity squared, dx. So we get pi integral from 0 to 4 of x to the 4th dx. And this straightforward integral has a value which you can compute, and it is 1024 pi over 5. Okay, let's look at another similar example, but will be a difference here. Let R be the region bounded by y equals x squared and the y-axis for y between 0 and 16. Suppose R is rotated about the y-axis to form a solid S. Find the volume of the solid S. So our region R here, it's the region that is bounded by y equals x squared and the y-axis for y values between 0 and 16. And so now we're going to rotate around the y-axis rather than the x-axis. And when we do this, we get this parabolic bowl. Again, we don't have to have the best artwork, but we do need to have our bearings on what the solid is, and then, or what the region is, and then what our solid is. And so when we do this, we have a choice of how we're going to slice this. It doesn't seem to make sense to slice this vertically, but since we rotated about a y-axis, it makes sense to slice that perpendicular to that axis so that we can get circular symmetry. We can use the circular symmetry to get discs. And so here I'll draw one representative disc, but I want you to envision many, many, many of these discs. I'll just draw one of them. We immediately see that it sits at some variable height. I'll call that height y that it sits at. And I see that the thickness here is delta y. It's a thickness in the y direction. And we also notice that it's a little disc or a little cylinder. And so the key feature here is we're going to need to know the radius of this disc. And so if you give me the y, the slice height, I can see that the associated radius is that length x. And that x is not random, but rather it's following the curve y equals x squared. And so if I want to solve for x in terms of y, since this is the curve y equals x squared, I can just rearrange and solve that to get x is equal to the square root of y, and now I know that that x distance is the square root of this y distance. Okay, so let's put that to work for us. Here I'll just pull off my representative disk. We'll say that the volume of the slice is the area of the face times the thickness. But the area of the face, this is just a circle. This is why we have nice consistency when we're doing solids of revolution here. When we get disks, we know that the area of the face is just the area of the circle, so it's a very straightforward geometry. We get pi times the radius squared. We said the radius of the disk was x, and then the thickness is delta y. We again read our keys. Because the thickness is delta y, we need this x written as a function of y, but we did this over here. And so we know that x is the square root of y, so we'll replace x with the square root of y. And now we're ready to accumulate the volumes of all those small slices, and we get the total volume is the integral. We'll deal with the limits in a moment of pi square root of y squared dy. So here we're just accumulating the volumes of the slices. And for our limits of integration, we know that our slices could be as low as y equals 0, and they're going to work their way up all the way to, they're going to top out at a y value of 16. And so we have the integral from 0 to 16 of pi square root of y quantity squared dy. We'll simplify that really easily to get pi times the integral from 0 to 16 of y dy. That's a straightforward integral that you can do on your own, and that'll come out to be 128 pi. So both of these are examples of the method of disks. We say the method of disks because when we sliced in the correct direction, we got a little disk or a little thin cylinder, a little penny if you will. And in order for that to happen, for us to get disks, it requires that the region R that we started with to be completely adjacent to the axis of revolution. So what we want to look at next are some examples where we have a region that we're going to rotate, but it's not completely adjacent to the axis of revolution, and that's going to cause us to have a slightly different geometry. Okay, so this time, let R be the region bounded by y equals x squared and y equals x, as shown below. Suppose R is rotated about the x-axis to form a solid S. Let's find the volume of the solid S. So here we have the curve y equals x squared. We have the curve y equals x. We're looking at the region that's bounded by those two curves. We've dealt with this region before, and we found these intersection points. We know that we're going to rotate this around the x-axis. And when we rotate this around the x-axis, we're going to get, I'll preserve this picture so that it doesn't get messed up as we do this, and we can look back on what the simple region R was. But when we rotate this region around the x-axis, we get, the way that I visualize this is I just look at a mirror image. This down here is just the mirror image of this. So I had this line, so I draw this line. I had this orange curve, so I draw its mirror image, its reflection around the x-axis. And then I know this is my axis of revolution. I give it a little bit of 3D effects just to have a feel for what's going on. And then I have to decide how I'm going to slice this. So we could slice this with horizontal slices, but it looks like it has a complicated geometry. Whereas if I slice it with vertical slices, I get to make use of this circular symmetry here, and I get these little, not discs this time, but I get these punctured discs or washers. And the reason we get washers is because you notice our region was not completely adjacent to our axis of revolution. So this air, for lack of a better term, is causing us to have a void in our solid. This part of our solid is the solid part, and then here this would just be a void that's in this funnel-shaped object. So if you looked at this object from the outside, it would look like a cone, but when you looked at it on the inside, it would have this arched interior. Okay, so when we slice this, we're going to get a little thin washer. Now my picture is going to get extremely busy if I label everything here. And it'll get so cluttered it'll be hard to see what's going on. So I want to be careful not to get my picture too busy. And I'll label some things here below in just a moment. So to get my bearings, this is the curve y equals x. This is the curve y equals x squared. This is my representative slice. My representative slice has a thickness in the y direction, which I'll show below. It sits at a variable distance x, and I know that these slices are going to dynamically be placed as we move along the solid in this direction. Okay? So when we do that, we see that, well, we need to find the volume of the slice, but to find the volume of the slice, when we look at this little very thin washer instead of a disc, washer because this has a hole in it, the way that we can find the volume of this slice is we want to find the area of the face times the thickness. Well, the thickness is delta x. And in order to find the area of the face, we just need to find the area of the big circle and then subtract from it the area of the little circle. Well, the area of the big circle is going to be pi times the big radius. And the big radius, which we'll call the outer radius, would be this distance here. It would be the distance from the center of the washer all the way to the top outside curve. And so that is just tracking this top outside curve. And so that, since that has the formula y equals x, this y distance, you could call it y, but this y distance is x. On the other hand, the inner radius is going to track this bottom curve. So this inner radius here is just going to be, it's also a y distance, but it's a y distance that's tracking this function, so it's going to be y equals x squared. So we'll label that below. The inner radius here is going to be a y distance, but it's the y that's following the curve x squared. The outer radius is going to be a y distance, but it's the y that is tracking the outer curve, and so that's x. So we just want to subtract. We can factor out the pi, because it's pi times the big radius squared minus pi times the little radius squared to get the area of this face of this washer. So we'll just factor out the pi, and we'll write this as pi times the quantity r outer squared minus r inner squared times delta x, the thickness. This tells me right away that my thickness is delta x, so that means these radii must be written as functions of x. My hand is forced here. They have to be written as functions of x, not functions of y. When I do that, the r outer was x, but I'm going to square it, so I get x squared. The r inner was x squared, but I'm going to square it, so I'll eventually get an x to the fourth. The parentheses here are very important. A key feature to remember is this is r squared outer minus r squared inner. It's not r outer minus r inner quantity squared. So each one of these has to be squared. That's very, very important. Okay, so now we're ready to do some calculus. Therefore, the total volume is just the integration or the accumulation of the volumes of these slices. So we're going to get the integral. We'll deal with the limits in a moment of pi times x squared minus x to the fourth dx, and we'll factor out the pi, and then our limits, well, since our slices are marching from here all the way over to here, you can go back and look at our region. That intersection point had an x coordinate of 1, and the intersection point here had an x coordinate of 0. And so we're going to be integrating from 0 to 1, and that's how we got the limits on our integral. This is a very straightforward integral to do. None of these so far have taken any fancy methods. So we can just integrate that, which you can do on your own, and you'll get 2 pi over 15. Okay, so the difference in this example and the previous one is that because our region R was not completely adjacent to its axis of revolution, we had a void here, and this air is going to create washers instead of disks. And so it's just a variation on a theme. So you have to be clear on what your region looks like so that you know whether you're dealing with disks or washers. Okay, let's look at another example. Here, let R be the same region as we had just a moment ago, but this time let's rotate R about the y-axis to form the solid S instead of the x-axis. So last time we took this and we rotated it this way, but now we're going to rotate this region around the y-axis so that we get a different type of parabolic bowl. Okay, so when we look at this, here I'm just going to try to visualize what's going on. This is my region R, this is y equals x squared, this is y equals x. I'm going to, since this is my axis of revolution is the y-axis, I'm just going to give it, draw the mirror image over here. So this line, its mirror image across the y-axis is here. This parabola, its mirror image is over here. I'm going to give this some shading so that I know that this is where the solid is. Notice my region is not adjacent to my axis of revolution. So all this here is air. That's going to create a void. That's going to create air here. And that means when we slice it perpendicular to our axis of revolution, so it wouldn't make sense to slice it this way. Instead, we want to slice it this way. And when we do make these horizontal slices, we're going to get little washers. So I tried to show what the inner ring looks like and what the outer ring looks like. I don't want my picture to get too busy, but I do want to label the important parts. So I drew one representative slice. If I can understand what's happening in one slice, I can extrapolate that to them all. And so that one slice has a slice height of y. We see that it has a thickness in the y direction, delta y. So now it's a matter of finding this inner radius here and then finding this outer radius here. So if you look at that for a moment, I can already tell that the inner radius is going to be a length in the x direction, and it's going to be an x that tracks this curve, the line y equals x. On the other hand, the outer radius is going to be a distance in the x direction, but instead of tracking to the blue curve, it's going to track to the orange curve. And when it does, we're going to be tracking this orange curve, y equals x squared. So here I'll pull off my slice. I'll label my thickness. I'll look at the outer radius. The outer radius is going to be tracking this. I know because my thickness is in the y direction, I'm going to need everything eventually in terms of y, not in terms of x. So this isn't doing me any good. I need to recast this by solving for x in terms of y, and now this x distance, this outer radius, is the square root of y. And on the other hand, this inner radius, this x distance, this inner radius, is going to be x equals y. So it's going to be y. If we put that here, we see that the outer radius is a distance x, which is the square root of y. The inner radius is a distance x, which in this case is y, and we have washers. Because we have washers, when we go to do the volume of the slice, we get the area of the face times the thickness. So we get pi times r outer squared minus r inner squared, delta y. The parentheses here are very important. Again, because this is a delta y, these guys need to be in terms of y, not x. But we did that already. R outer is the square root of y, and we're squaring it. R inner is y, and we're squaring it. So now we're ready for the calculus. Therefore, the total volume is the accumulation of the volumes of the slices. So we get pi times, we'll do the limits of integration in a moment, the square root of y squared minus y squared dy. And then we are integrating from 0 all the way up to 1, because that was the y coordinate of the intersection point there was 1. I know that the x coordinate was 1, but it has nothing to do with this one. It has to do with this one, because our slices are dynamically proceeding in this direction. The slice heights could be as low as 0, and the slice heights could be as high as 1. That's what the y represents, and that's what this y is representing. Y ranges from 0 to 1. So when you simplify this, we get the square root of y squared is y, and then this was already just a y squared, and we have a straightforward integral here that you can do on your own to get pi over 6. Okay, let's look at another example. And this time we want to vary things just a little bit by looking at what happens when we rotate about what I call an offset x or y axis. So we're going to rotate around something that's not the x-axis or the y-axis. It's still going to be either a horizontal or a vertical line, but it won't necessarily be the x-axis or the y-axis. Okay, so let's let R be the region shown below. So we keep picking on this region that is bounded by here this parabola y equals x squared, the y-axis, and the line y equals 16. So suppose S is the solid form this time when R is rotated about the line y equals minus 2. So we're not going to rotate around the x-axis, but now we're going to rotate around. So notice the x-axis is just y equals 0, but we're rotating around the line, say y equals minus 2. If we understood how to play the game with what we were doing before, this will just be a slight variation. So we don't want to try to memorize formulas or anything like that. Instead, if we can understand the concept of what's happening, we can adapt to whatever situation is presented to us. So again, we need a clear idea of the geometry here. So we have our region R. We see that we're going to rotate this around the line y equals minus 2. So be careful, this is the x-axis, but this is y equals minus 2. I'm just going to draw the mirror image. So the mirror image of this is this. The mirror image of the orange curve is this. Notice this was 2 units away from where my region began, so this ought to be 2 units away. There's a little gap here. And then it doesn't make sense to slice things like this, but since we were rotating around a horizontal axis, we want to slice perpendicular to that. And we see that if we slice perpendicular to that, we get these, again, we get washers. We have washers because our region is not completely adjacent to our axis of revolution. As a matter of fact, it's not adjacent at all. Okay, so when we do this, we just want to take a look at what our inner and our outer radius is each time. Okay, so we'll start with the outer radius, and our picture is very busy, so I won't mark it up too much, but our slice here sits at some representative slice sits at some distance x, we'll say. And then we see that our inner radius, we want to be careful. This normally would be our inner radius, but this time our radius is not centered around this axis, but it's centered around this axis. Now my picture is not perfect, but I do want you to realize that our radii are being measured from this black line, not from the x-axis. So this can be a little tricky, but here's, I think, a foolproof way to know how to find what the inner and the outer radius, what those values are, what those functions are. So what I want you to do is just look at, we want to find this outer radius, I don't want this distance. I actually want this distance. So notice I want the distance from the black line all the way up here. Now here's some things I know. I know that this distance from here, the x-axis, to here, that's a distance of 16, because this is y equals 16. So what I want to do, I can see that I have 16 and I want to add 2 to it, but you can have different situations, and it may not be that clear, that easy for you to be able to see. So here's a foolproof way that you can tell. I really want the length of this line right here. And the length of this line is just the top curve minus the bottom curve. The bottom curve in this case is the curve y equals minus 2. So in order to find the outer radius, I just want to do top curve minus bottom curve. Top curve has a formula of y equals 16. Bottom curve has a formula of y equals minus 2. So I just want to do 16 minus a minus 2. That's going to give me 18. And that's consistent with what we said. If this distance is 16 and we want to add this little offset to it, we see that we're adding to our radius, and so we should get a bigger radius, and we get 18. Okay, if we play the same game for the inner radius, we don't want this distance. We want this distance from the black line to the top of our inner radius of our washer. So again, we want to do top curve. Notice top curve in this case is the orange curve. So this is y equals x squared. So top curve is x squared. Bottom curve is minus 2. So we want to do x squared minus a minus 2 to get an x squared plus 2. Now that we have the outer and the inner radius, we just do what we've done before. The volume of the slice is pi times r outer squared minus r inner squared. The thickness here again, from our picture, our thickness is in the x direction, so it's delta x. This is a washer, of course. And because this is a delta x, I know I need these guys in terms of x, or I can't afford to have them in terms of y. We already found that r outer was a constant. It was 18, but we're squaring it. And r inner was x squared plus 2, but we're squaring it. Okay, so now we're ready to do our calculus and to find the total volume. So we just take the accumulation or the integration of the volume of our slices. So we have pi times 18 squared minus x squared plus 2 quantity squared dx. That's an integral that you can do. Here I would just multiply this out, simplify, then it becomes a straightforward power rule with linearity, and when the calculus dust settles, you get this value for the volume of the solid. Okay, one more example. So since we've done an offset in this example, we did an offset x-axis. Why don't we finish it out by doing an offset y-axis? By now we should be familiar with the game, but we just want to see how the details change as we deal with an x-axis or a y-axis, an offset x-axis or an offset y-axis. So let's take the same region R, but this time let's rotate it about the line x equals minus 2. So we have the same region R. We're going to rotate about this offset y-axis. We'll say x equals minus 2 to form a solid S. Let's find the volume of S. Okay, so we're pretty experienced at doing this by now. So again, I want to get my bearings. I have my region R. I see that it is not adjacent to my axis of revolution. Because of that, I know that I'm going to have washers. So to visualize what the solid looks like, I'm just going to do a mirror image of this around this line. So here, with this straight line boundary, I'm going to get a straight line here. This parabolic boundary, I'm going to get a parabolic boundary here. Then I just give it a little 3D effects, and I can see that I get this parabolic bowl that has this void in the middle. This is why I shade this, so that I can be clear of where the solid part is and then where the void is, because that's going to dictate my inner and my outer radius. It doesn't make sense to slice it vertically. Since we rotated around a vertical line, we want to slice it perpendicular to that axis to make use of the symmetry, the circular symmetry here. So here I'll just draw a representative slice. When we do that, I see that the slice is going to have a thickness in the y direction. We also see that you're going to have an inner circle and an outer circle. So this is going to be washers. I want to be careful here to track. This is going to be the inner radius, and this is going to be the outer radius. Now I have to be careful because these formulas never measure anything from an offset axis. They always measure things from the x-axis or the y-axis. That's our standard coordinate system. So I'll show the slice height here is y. And so if I have this y, I need to find out what this length is. And again, our foolproof method for doing this is don't overthink this. Don't try to memorize formulas. All you have to do to find the outer radius, this length here, you just need to do right curve minus left curve, and the left curve here is our curve x equals minus 2. So I need to do right curve minus left curve. I see since my thickness is delta y, I need everything in terms of y, not x. So I'll go ahead and I'll quickly resolve, and I'll get that if y is x squared, then x is the square root of y, and that tells me that this x distance is the square root of y. Not this distance, but just this distance is the square root of y. So to find the outer radius, I want to do right curve minus left curve. So I do square root of y minus the curve here is minus 2. So square root of y minus a minus 2 gives me square root of y plus 2. Similarly, to find the inner radius, I just need to do right curve minus left curve, and the right curve in this case, we're tracking this line. This is the line x equals 0. This is the line x equals minus 2. So I want to do 0 minus a minus 2, which gives me 2. And that makes sense, right? The inner radius on all of these is the same, and this is always a distance of 2. The inner radius is not changing. Okay, so we're ready to find the volume of our slice. It's pi times r outer squared minus r inner squared. The parentheses are very important, delta y. Once again, if we just are doing our little checks as we go through this, since our thickness was in the y direction, we know that these guys have to be in terms of y, but we did that already. And so our r outer is the square root of y plus 2, but we're squaring it. And then r inner was just 2, but we're squaring it. So then our total volume is just the integral or the accumulation of the volumes of our slices. So the volumes of our slices, dy. And for our limits of integration, we just need to realize that y could be as small as 0. That's our slice height. It could be as small as 0, but our slices are going to dynamically proceed till they get to the top of this region, and the top of this region was y equals 16. So we're going to integrate from 0 to 16 of pi times square root of y plus 2 quantity squared minus 2 squared. The parentheses are very important. If you look at that integral, I would just square this out, combine my like terms here, and then you should get a straightforward integral that can be done by linearity and the power rule. And when the calculus dust settles there, you can check. We get a volume of 896 pi over 3. So when you go to do the homework, I know that there's a lot of examples in here, but I wanted to try to give you a look at all the different things that you could see. And if you back up to the beginning, we had the method of disks. We had disks where the thickness was in the, let's go back to the very first example. We had disks where we integrated in the x direction. We had disks where we integrated in the y direction. Then we had washers where we integrated in the x direction. We had washers where we integrated in the y direction. And then we had washers where they were washers that came about because we had an offset axis. So here we gave you washers with an offset x-axis, and then I showed you where we have washers but through an offset y-axis. So you've seen all the combos, and you ought to be able to do all the homework problems based on these.